So guys, in this video we'll be discussing about the errors in the instrument transformers. So we'll be looking at the current transformer and the potential transformer. So as you know, a transformer has its equivalent circuit. We have drawn the equivalent circuit over here. Let's consider this as a transmission line, right? Over here we have a transmission line and the CT is connected over here across these points A and B. Let's call this A and B. So we have a transmission line and a current transformer connected over here across the points A and B in order to find the current passing through the transmission line. So let's say so I hope you guys already know about the equivalent circuit of the transformer. So I'll give you a small briefing about what is the how is the equivalent circuit of the transformer. So here we can see this is R1. Now R1 corresponds to the primary side coil resistance. X1 corresponds to the primary side coil reactance, and then you have R0 and XM. R0 corresponds to the core losses. In case of air cooled transformers, R0 will disappear, but in case of normal transformers, there would be a certain amount of core loss that is associated with the core of the material. So R0 is the core loss, and then XM is the magnetization loss for the magnetization of the transformer. And then we have the secondary side resistances, or the coil resistance of the secondary side as R2, which is multiplied with the turns ratio, square of the turns ratio, because we are referring it to the primary side. And then we have A square into X2, which is the square of the turns ratio multiplied with the secondary side reactance. So since we are referring it to the primary side, we have this A square factor over here. And then finally we have the ideal transformer on the right. Ideal transformer means there is no losses and the transformation ratio is very much perfect, which is N1 by N2 is equal to V1 by V2, or we can also write I1 N1 is equal to I2 N2, right? From here we can see that we'll be connecting an ammeter to the secondary side of the current transformer, and from there you can measure the current readings. So the ammeter reading over here would turn out as the ammeter reading in this particular circuit would be I2 amperes, and which can also be written as A into I1. I1 is the current in the primary side, but then in this circuit that is not actually true, because I1 is over here. So actually it is going to be this is actually I2 is actually A into I2 dash, which is over here, right? So and this is not true for this case. It is actually A into I2 dash, which is the current that is coming to the primary side of the ideal transformer, because there is a current which is going to the I0 that is splitting over here. Therefore I1 is not equal to I2 dash, and therefore I2 is not equal to A into I1. So from here if you want to find what is I2 dash, so I2 dash would be the primary side current, primary side current would be equal to I2 dash, that is equal to I2 divided by A. A is the turns ratio, as we already know. A is N1 by N2. So from here we can clearly see that we have already seen from the circuit that I1 current is getting splitted at some point, and there is a current which is I0, and then there is the other current which is I2 dash, right? Which means that I2 dash is not equal to I1 in this case. So there is definitely a error. How much is the error? The error over here is I1 minus I2 dash, which is equal to I0 is the error in the calculation, right? So from here, from the circuit, you can see I1 is the current that is flowing through the primary side, or that is the current that is going through the transmission line I1, and in the this is the I0 current which is going parallel, because of which I2 is not equal to I2 dash is not equal to I1 in this case. Therefore, when you calculate the current, there is always a small error associated with it, and the error is I0. So here the other factor that you will have to consider is that there is two types of error in this case. One is a ratio error and the other one is a phase error, because I0 has a particular phase. So let's look at the phasor diagram. So we won't be going into the detailed phasor diagram. We'll be drawing a very rough phasor diagram for this circuit. So I0, we'll take it in this direction, and I2 dash is roughly in this direction. Therefore, if we connect these two phasors, the vector sum, if you take the vector sum of these two phasors, you will get I1 in this direction. Now here you can see that the magnitude of I1 is also greater than I2 dash, and definitely there is a small phase angle difference. Let's call it theta. So there is a small phase angle difference also over here between I2 dash and I1. So there is definitely there is a magnitude error or a ratio error. So magnitude of I1 is not equal to I2, which means there is a ratio error, and the angle between I1 and I2 dash, sorry, it's not I2, it's I2 dash, and also the angle between I1 and I2 dash is also not equal to 0, which means that there is a phase error. Now in terms of normal CT, where you are only measuring the current, this phase error is not relevant, because we are only concerned about the magnitude of the current. So the phase error doesn't come into play. But in case if you are measuring power, or in case if you are measuring energy consumption, in that case definitely the phase error will have a significant role, because you will be using current transformer and a potential transformer in tandem, in the same place, and therefore there would be, if there is a particular phase difference between the voltage and the current measured, then there would definitely be a phase error that will cause the calculation of the power rating, or the power that is consumed, right? So in this case, if you are only measuring the current, then that is not much of a problem. The phase error is not a problem. Only the magnitude error, this is the magnitude error. The magnitude error is of concern. Okay. Now how can we minimize this magnitude error? To minimize the magnitude error, we'll have to maximize the resistance, the R0 resistance in the circuit. You can see, if you maximize these two values, what happens? The permeability of the core also increases, as well as the low core losses will also be there. If we increase R0, the current through the resistance will decrease, and therefore you will have a very low core loss, and also the error will also decrease, because since the current decreases in R0, there will be a very less amount of current that will pass through the R0, therefore the error also decreases. Similarly, if Xm is the mutual inductance or the magnetization reactance, you can call it as the magnetization reactance or the mutual inductance. If we increase, what happens? The permeability of the core increases, right? Permeability increases, which means that with less amount of current you can have proper magnetization of the core, right? So with less amount of current you will have proper magnetization, therefore you can minimize the error in this case. Now the main way in which we compensate this error is that, or the manufacturers of compensate this error is that, they use a technique called turn compensation. Turn compensation. So here we have already seen that the magnitude of I1 is, what is it, is slightly greater, right? Slightly greater than the magnitude of I2 dash, right? So what we do is that, so here the true value, basically what we are getting is that the true value is I1 is slightly greater than the measured value, right? The measured value, right? So measured value is the I2 dash. We measure I2 and then we divide it with A in order to get I2 dash. So the true value is slightly greater than the measured value, and in this case what we do is that, let's say what we do is that N1 is to N2 is the nominal turns ratio, or that is the turns ratio that is given to us. But the manufacturers, what they do is that, in order to slightly compensate this error in the current, what they do is that they keep N2 the actual value of N2 slightly less than the nominal N2, which is over here, in order to compensate this this error that is there. So here we can see I1 N1 is equal to I2 N2. If we reduce the number of turns in N2, what happens is that you will get I2 slightly higher than the actual value. So that is how we compensate this particular error that is there in the I0, due to the current that is leaked as I0. We compensate this in terms of using the turns compensation method. So, and some various few points that we need to consider while operating a CT. We'll be mentioning some of the major measures that you have to take while so these are some of the precautions while operating a CT. So these precautions are corresponding in case if the current transformer is connected to a large transmission line. Now these are some of the precautions, but we'll also see that currently we don't actually use the conventional types of CTs. We use clamp-on meters, in which these problems are not faced. But in conventional types of CTs, let's say if you are having a transmission line, and from the transmission line, if you are let's say in the similar case, let's say you have all the resistances, inductance, then there is a resistance, there is a inductance, right? So I'm not drawing it very clearly because we have already drawn this figure. So here what we need to take care is that we always will have to have a parallel circuit with a small resistance. The reason is that we'll have a switch over here and another switch and an ammeter. So this is how a conventional CT is connected. Now let's say you are not supposed to, in conventional CTs, we should never open circuit the secondary side voltage, secondary side load. If it is ammeter, you need to keep it connected, or let's say if it is let's say Z is the secondary side impedance. So if you make this infinite, which means that if you open circuit this side, what happens is that there is a, towards the primary side, it will be reflected. This is AB, across AB it will be reflected as A square into Z, which is again very high because of the open circuit on the secondary side. Now if you have a if this is happening, what happens is that there won't be any current that would flow through the primary side of the ideal transformer, and all the current will have to flow through this circuit, because the primary side current is basically dependent upon the current that is drawing from the secondary side, right? And the magnetization current is over here, which is the I0. So what happens is that in general, what happens in the transmission line, you will have a huge resistance or huge impedance due to the CT itself, which will load the transmission line itself, so which is not desirable at any cost, at any case. And the other case is that this could also lead to the damaging of the CT also, because since there is a high impedance and there is a high current that would flow, there will be heating, and heating could takes place in the CT, in the primary side of the CT, and a high voltage also will appear across the primary side of the CT, which can destroy the instrument itself. So in that case, in case if you want to change the ammeter, or if you want to do any kind of such operations, first what we do is that we'll connect this load, a small load, onto this current transformer, and then we can open the switch over here and replace the ammeter with some other ammeters or anything. Then you can close this switch over here and then open the load, parallel load that is connected. So this is how you will have to operate a CT, a conventional CT, which is connected to a transmission line, because you don't want to affect the transmission line at any cost, right? So we always want to have a very small voltage drop in the transmission line, and we don't want because if there is a very small resistance on the secondary side, there would be no resistance transferred to the primary side, because of which there will be high current which will pass through the primary side of the transformer, and a small current will be used up in the magnetization of the transformer. So that is the desired operation of a CT. And other problem is that the high voltage on the primary side could also reflect a very high voltage in the secondary side, because a current transformer is a step up voltage transformer. CT is a step up voltage and step down current, right? Here in the secondary side the current will be low, but the voltage will be high, the power remains constant, right? So if there is a huge voltage that is appearing over here, that implies that there will be a huge voltage that will appear over here as well. So the moment there is high chance of risk in conventional CTs if you keep this open circuit. So that is one major disadvantage over here in case of CTs. But in modern days we are using clamp on meters. Clamp on meters means you can there is something like a clamp, so you can say this. So this is a joint, so this can be opened, so and this can be opened, and the meter looks somewhat like this. It's similar to a multimeter kind of stuff, and you will have a something to press over here with which you will be able to move this to this direction, and then you can clamp it to any circuit, and from there you can find, basically this is also a CT which is a much more safer one, and you can clamp it to a transmission line or any line, and you can find what is the current reading, right? So similar to a multimeter kind of stuff. So these CTs will definitely reduce the risk, such risk, because you don't have to keep it connected, nor do you have to have a primary side coil over there. It takes it as a one coil on the primary side, and then you get a corresponding reading on the CT. Now let's look at what is the how is the error that is there in a PT. So error in a potential transformer. So in potential transformer also the concept is very same. There is not much of a difference in the potential transformer. We are going to go with the same conventions. So what we do is that you have a transmission line or whatever generating source. So from there you take a parallel connection. So this is the transmission line that is going up, and you have a CT across these points, sorry, a PT across these points A and B. A similar equivalent circuit will come up for the PT as well, and so these are the primary coil resistances, these are the core loss corresponding to the transformer, and the magnetization reactance corresponding to the transformer, and then you have the secondary side resistance, secondary side reactance, and then you have ideal transformer. So this is our ideal transformer. So here we'll have a voltage V, and what we do is that we'll step down the voltage and try to find what is the voltage over here. So that's how we are going to do in a potential transformer. So here the voltage is, let's say this is V2, and the voltage over here is V2 dash, which is A times V2. A is equal to N1 by N2 as the N1 number of turns, into number of turns, right? So is equal to v1 by v2, or you can, here in this case it is here it is v2 dash, sorry, v2 dash v2 dash by v2. So here, from here we can see that v2 dash is equal to n1 by n2 into v2, n1 by n2 into v2, or you can write it as a into v2, right? So here the measured voltage over here is v2, and the estimated primary voltage will be equal to a times v2, which is equal to v2 dash. But the problem here is that the voltage across A and B can be written as v1, which is not equal to this v2 dash, because there is a drop over here. There is an entire drop in these region, which can be written as vd, right? So so let's call this entire drop between v1 and v2 as vd. So basically what happens is that v1 is equal to vd plus v2 dash. So the true value is equal to the voltage drop plus the estimated value. In this case, so in this case also, these are these are vectors, v2 dash and vd, both are vectors, and we are not going to look into the detailed analysis of these vectors. We'll draw a rough diagram of these vectors. So let's say this is v2 dash, and vd is somewhat let's say in this particular angle. Here is resistance and inductance, reactances in this loss, and this is the equivalent vector, which is v1. So definitely there is a magnitude error and also a phase error. So what we do is that we do a turns compensation in this case as well. So as we have done in the previous case, what we do is that we'll do a slight turns compensation in order to get a perfectly or you can say in order to get a much more closer value to the true value. So turns compensation is the main method that is used over here in order to compensate this error, right? So we have already seen the turns compensation, how it is done. So in this case also we do the same technique, we use the same technique in order to compensate the error in this case, in order to overcome the voltage drop actually, or nullify the voltage drop in this case. So what we do is that we try to get the estimated value a bit more higher value than the normal value, so that we get an exact amount of voltage corresponding to the true value. So here in the previous case, I think we decreased the number of turns of n2. The same can be done over here, or we can increase the number of turns of n1. Anyone sorry so now what we are going to do is that we are going to we can just write this equation, so we'll get a clear idea. V2 dash into n2 is equal to n1 into v2. So what we need to do is that we need to increase the v2 voltage, or we need to get a slightly higher voltage with v2. So what we do is that we'll slightly decrease the number of turns in n1, by which we can get a slightly higher voltage in v2. So this detail won't be given in the potential transformer. It will have a proper nominal turns ratio given in the potential transformer, but the actual number of turns will be a slightly different in order to compensate this error. Guys, I think this video is clear, and the error analysis is also clear, I guess. So I will wind up with this right now over here. We'll meet in the next video. Okay guys.